Astronauts exercise 2 hours every day in orbit. Not casually. Resistance training and cardio, daily, on specialized equipment, with a whole support team designing the program around them. And they still come home with weaker muscles, thinner bones, reduced aerobic capacity, and measurable mitochondrial stress. I find that genuinely humbling, and I think there's a lesson in it that applies to people who are never going anywhere near a rocket. So let me walk you through what the research actually found, and then be careful about what it does and doesn't mean. Let's start with the big study. Researchers ran a large multi-omics analysis. That means they didn't look at one measurement. They pulled together gene expression, protein levels, metabolites, and epigenetic markers, from a lot of sources at once. The sources were substantial. Biomedical profiles from 59 astronauts. Hundreds of samples from NASA's genetic database, including mouse tissues, human cell models, and human tissues that had been flown in space. And the NASA twins study. Then they asked a simple question. Across all of these different systems and organisms, what keeps showing up? The answer was mitochondria. Their conclusion was that mitochondrial stress is a central biological hub for spaceflight impact. They described it as a consistent phenotype of spaceflight. Not one finding among many. The thread connecting the rest. And the rest is a long list. Astronauts returning from the space station have presented with bone and muscle mass loss, central nervous system issues, immune dysfunction, and cardiovascular risks. Researchers have compared the overall picture to geriatric stress. Now let me tell you about the twins study, because the design is beautiful. 2 identical twins, both astronauts. One spent a year on the space station. The other stayed on Earth as a genetically matched control. That's about as clean a comparison as human biology allows. Same genome, same age, one variable. In the twin who flew, the researchers found higher levels of mitochondrial RNA during the flight compared to before and after. And the amount of time he'd spent on the station correlated with that increase, with a correlation coefficient of 0.84. That's a strong relationship. The longer he was up there, the more of this signal appeared. They also found something that connects directly to a video I made last week. Increased mitochondria in his blood. If you saw that one, you'll remember there are hundreds of thousands to millions of whole mitochondria floating loose in healthy human blood, and the debate about whether they're functional. The best current evidence says they're probably not producing energy, but researchers propose they might be acting as signals. Distress messages, and here we have exactly that pattern. A body under sustained stress, releasing more mitochondria into circulation. That's not proof of the messenger hypothesis. But it's consistent with it, and I thought it was worth pointing out. Alright. So what's actually causing this? Here's the interpretation I find most useful, and it goes beyond space. Gravity is a signal. We don't think of it that way because it's never absent. But every second you're on Earth, every cell in your weight-bearing tissue is receiving mechanical information. Load. Compression. Resistance. Your bones are being told they're needed. Your muscles are being told they're needed. And your mitochondria are downstream of all of that, because tissue that's being used needs energy production maintained. Take gravity away, and that constant background message stops. The body responds the way it always responds to a signal that stops. It winds things down. It stops maintaining capacity it appears not to need, and this is where the humbling part comes in. Astronauts train hard against this. 2 hours daily is the standard. And the honest assessment in the literature is that historically, space station exercise countermeasures have not fully protected astronauts' musculoskeletal and cardiorespiratory fitness. In the earlier era it was worse. Astronauts spent up to 10 hours a week exercising and continued to lose muscle mass and bone density. Things have improved. A more recent study using a high-intensity, lower-volume program measured a 6% decrease in aerobic capacity from pre-flight to post-flight, compared with roughly 15% in an earlier study of station crew. That's real progress. It's also not zero. And I want to flag how the researchers themselves handled it, because it's a good example of honest science. Rather than declaring victory, they wrote that these outcomes now allow them to consider, for the first time, whether the exercise countermeasures are sufficient, or whether more optimization is needed. And they asked directly whether complete mitigation is even the goal. That's the right posture. Better, not solved, and here's the open question. Now I have to slow down, because there's an easy misreading of everything I've just said, and I don't want to leave you with it. The wrong conclusion is exercise doesn't work. Space is not just weightlessness. There's radiation exposure up there, which damages DNA and mitochondria directly. There's a continuous fluid shift toward the head. There's disrupted sleep, altered light exposure, confined living. Those are separate insults, and exercise wouldn't be expected to fix all of them. To isolate unloading specifically, researchers used bed rest studies on Earth. Head down tilt bed rest, for weeks or months. Same removal of loading, none of the radiation. And in a 60-day bed rest study, a high-intensity jump training program was successful in preventing loss of bone mass, muscle mass, strength, power, and aerobic capacity. The control group lost up to 50%. Read that comparison again, because it's the most encouraging thing in this video. When unloading was the only variable, the right kind of training prevented the losses almost entirely, while people who did nothing lost up to half. So the honest summary is this. Unloading is a powerful signal to wind down, and it can be countered, but the countermeasure has to actually involve loading. Which brings me to today's free lever, and it's more specific than what I usually say. It's not just move. It's load. Jumping. Stairs. Carrying something heavy. Anything that puts impact and weight through your legs and spine. That's the specific input those bed rest studies used, and it's the specific input that's missing in orbit. And here's the encouraging part. You already have gravity. It's working on you for free, every second, whether you think about it or not. Astronauts are trying to manufacture from scratch what you get by default. The question is only whether you're adding to it or slowly opting out of it. Now, where does my own recommendation sit today? And it's narrow. Everything in this video points at mitochondrial stress. CoQ10 is one of the carriers in the electron transport chain, the machinery that's under stress in all of these findings. Levels tend to decline as we get older. But I am not going to tell you a supplement protects against any of this. Nobody has tested that, and given the topic, that would be a very easy claim to slide in. There's no astronaut study on it and there's no bed rest study on it. If you want to support that machinery on the same narrow grounds I always give you, the link in the description below is an affiliate link to Mitochondrial, which is PQQ and CoQ10, with a 90-day money-back guarantee. And if you want more videos where the striking finding comes with the reason not to overread it, subscribe. This video is educational only and it's not medical advice. Talk to your doctor before starting new or higher impact exercise, especially if you have joint problems, bone density concerns, or you've been inactive for a long time.